They, through some patent breaks, they brought it from a unethical company, stole it from a New Zealand guy that designed it, changed it so they wouldn't have to pay him a royalty, and turned it from a good tool into a horrible tool. If you need weight to keep something in the ground, don't use it, is the bottom line. With herbicides, how do we mitigate or lower the damage caused by herbicides? Well, one of the big ones is to rotate modes of action. Don't overuse one tool. Even though some things may be different, they all have a little different aspect on the damage they potentially could do. So by rotating modes of action, not only do you not end up with weed issues with your the nasty stuff we hear about, Palmer amaranth and all of that, which we don't see much of up here yet, but it can be coming if we don't watch it. The other issue with herbicides is don't be afraid to lower the rate. And I know this is heresy from the aspect of resistant weeds, but if you're rotating modes of action, that's not as big a deal. And 100% weed-free is not really the goal. You want to lower the impact of your native volunteer species to where it's not damaging your yields, but going completely clean, completely weed-free is not a worthwhile goal. And on the fertilizer, on this one, don't guess, test. And I like not only soil tests, but forage tests. If I had to choose between the two, I would take the forage test or any kind of plant test, because that's telling me more about what's actually available out there, what's actually coming to the plant. That's really the important part of fertilizer, is what the plant's getting. Making a pretty looking soil test is not economically viable. If you do a good job with your plants, you'll get there on the soil test, but don't aim for balancing that soil test unless you know what the plants need. And then of course there's some fertilizers that are more destructive than others. There's some that are beneficial and some others that can feed the plant at the destruction of the soil. One we don't see a lot, I don't know how it is out here in central New York, I don't see much of anhydrous ammonia. That's one that should have never been touched by, should have never been a fertilizer. And I'll give you an illustration of why. It's heavily used in the Midwest. I lived for 8 years in southern Indiana along the banks of the White River. Well, the White River drains probably over half the state of Indiana. It's 400 or 500 miles long, and in its entire length, I think the total fall is around 300 feet. It's flat. Well, I was there a couple years after I was living there in Indiana. I was talking to an old neighbor, an old timer that had been farming there all his life, and he told me that 25, 30 years ago they brought loads of alfalfa out of the river bottoms, and it would have been great soil for alfalfa. It was well drained, it was kind of a gravelly texture, well drained soil, naturally high pH. The river was naturally a higher pH, and everything was perfect for growing alfalfa in those river bottoms, except in the 8 years I lived there, the river flooded during the growing season 6 times. So what changed in the 25, 30 year period? It wasn't the weather. Might have been some changes, but it wasn't that dramatic. What changed was the water holding capacity in northern Indiana. It's the only thing I could figure it was. And I talked to people in northern Indiana that would agree with that. The water holding capacity went out the bottom. So that's the impact of some of these tools that agriculture in general uses without really looking at the long-term impact. And as I said before, this is the big one. Biomass and photosynthesis. This is what drives the system. So to really move forward, we got to concentrate on getting this one right. Sugar production is what drives the system, and it has two components. First, we've got to have the plants out there growing. That's the biomass part. And then we've got to make sure those plants have the nutrition they need to photosynthesize and produce sugars beyond what they have to have for their own growth. Only when they have some excess can they feed soil and make the root exudates and everything happen. So the two points of plant density and plant nutrition is what drives these two. In plant density, of course, we all understand as farmers the importance of getting seeding rates, optimal seeding rates applied, getting our seed beds in good shape, and doing everything possible for a good crop. We all understand that. Where a lot of farmers in general kind of lose on this is by not keeping the soil covered enough of the year. I think we're going to have to, in some cases, shorten down our cash crop in terms of his corn, back off the day length a little bit to allow more time to get some crops established. Get some more crops in the rotation, utilize the shoulder months, keep something growing. It won't necessarily grow in the winter, but the roots will be growing in the winter. Keeping the soil covered as long as possible is what really makes a difference. And then, of course, focusing in on the nutrients that drive it is also part of it. Here are the 5 nutrients that are directly related to photosynthesis. Now right here is the slide where I usually ask the question about which is the most important nutrient in plant growth. We've already covered that one. It's actually carbon. But nitrogen, magnesium, phosphorus, iron, and manganese. Any of these 5 can short circuit the photosynthesis sugar production part of plants. Phosphorus is not directly related to directly utilized in photosynthesis, but it is a key element in transferring sugar. If you don't have enough phosphorus, you're not going to transfer the sugar that's being produced and get the benefit out of it. In fact, a lot of you are familiar with what a phosphorus deficiency looks like in, say, early season corn. It's the purplish color of the leaf. What that purple actually is excessive sugar buildup in the leaf. The photosynthesis process is working fine. The sugar is being generated, but it's not being moved down to the lower in the plants and out the roots like it should be. And that's due to the low phosphorus. And then the 2 micronutrients here, iron and manganese. Typically we have enough iron. Sometimes we'll benefit from applying some. But I often see a shortage of manganese. It's something that's it's being ignored in a lot of places. And if manganese is low, that can often be the limiting factor. In fact, nitrogen, people look at nitrogen all the time as being a limiting factor in production. Sometimes it is, but more often it is not. Even in wet situations like we saw last year where we have a lot of nitrogen leaching, even in those situations, often nitrogen is actually not the limiting factor. Because nitrogen, somebody mentioned oxygen earlier. Nitrogen and oxygen as visual symptoms are indistinguishable one from another. In 2015, it was a fairly wet year over in my area. I'm not sure how it was here. I pulled some tests off of corn that was textbook nitrogen deficient. It looked, as a V firing in the lower leaves. Any expert could have walked in that field and said it was short of nitrogen. But it wasn't short in nitrogen. It had plenty of nitrogen. What it was short in was oxygen. Found out later on through official at the USDA that, and that was new information for me, but oxygen deficiency and nitrogen deficiency is identical. You can't tell the difference in the field. However, one of the things that you'll see with nitrogen, sometimes the symptoms go away even though that wasn't a deficiency. But the symptoms go away because nitrogen, a chemical nitrogen application on the soil will react with the soil, react with the carbon. It'll release more carbon dioxide, which is one of the reasons we see such a green up response from nitrogen. Not the only reason, but one of them. And in that process, it also releases more oxygen. So the plant gets an oxygen boost in the soil itself, in the root zone. So just because you see a result, and that's one of the things I find sometimes research falls down on by not checking enough variables. Just because you see a response from doing something doesn't mean that it did what you thought it did. Sometimes it did, but not always. There's a lot more, sometimes there's more variables than what we're looking for. Now, the winter meetings I did this presentation at, they were all forage orientated, which I assume this is a little bit too. And I asked the group, why do you think I'm throwing a blueberry photo up here in a forage meeting? Well, the answer to this is the best photo I had illustrating a really high energy plant. If you look at these, if you know anything about blueberries, you'll see that these leaves are larger than average, thicker than average. They have a nice glossy, waxy sheen that kind of shows up on this photo. And there's one more thing that shows me that this plant is exploding with energy. See how many of these blueberries are ripe? None of them are overripe. That whole handful, except for a couple of outliers, is ripe and ready to harvest. A multi-fruiting plant like blueberries, your tomatoes, all that type of thing, if it has got all the energy it can use, it will express it in the whole cluster ripening at once. Now, the question is, how do we get to this level of energy? Well, it all starts with the sugar production, but then the sugar feeds biology. The biology mineralizes the soil, makes the minerals available from the soil profile, available to the plant. The plant, as it builds levels of energy, starts building more fat. We have, as animals, humans, everything in the natural environment, excessive energy gets stored as fat. Plants are no different. They have more energy than they need for the process at the moment. They store it as fat. What additional fat does then, that's what really drives the long-term stable soil systems, because fat in return is not digested by bacteria. Fat is digested by fungi. And Dr. William Jackson, in his book Organic Soil Conditioning, makes a point that between 40 and 44% of all your stable humus in the soil is derived from lipids, derived from fat. So what that means in real terms, looking at a cover crop like this, if you have, just to make up a number, doesn't really matter, say 10,000 pounds of biomass out there, and the fat content moves from a baseline of around 2, which is about as low as plants go, to 6, which is getting quite good, you have the potential of building 3 times as much stable soil organic matter out of that crop. It all comes back to the fats. But to get to that point, you got to start with the sugars. The sugars are what the plant produces to feed the biology. The biology mineralizes the material, makes it available to plants, and then as the energy builds up, they can start adding fat. Now, fat has a lot more advantages than just building soils. Higher fat means higher energy. If we're looking at a forage crop, you hit a 6% fat and you can start really cutting off grain without reducing milk production. At somewhere between 8 and 10% fat, cows won't even touch grain if you give them the choice. And I heard about this a few places, and actually met a guy over here in the Finger Lakes region that was at one of our winter meetings. He came to me afterwards and said, yeah, I know exactly what you're talking about. My cows last year had been the spring of 16s when he saw the best results. He had some forage in his pasture that was measuring at 10% fat. He was producing 70 pounds of milk and no grain at all. His cows weren't losing condition. So the energy is there if you can get it into the plants. Then we get into fruit and vegetable crops. that extra fat really builds a lot of disease immunity. A lot of your diseases can't attack the plant through a layer of fat. So it's important all the way around. But again, to get there, we got to start with this. This is, I've seen this phenomenon numerous times digging around the soil, but this is the only time I was actually able to get a decent photo of it, because these corn plants growing in about 2 weeks away from tassel, kind of at the tail end of their big growth spurt, they were pushing out so much sugar, so many root exudates, they couldn't even wait till the roots hit the ground. They were shoving it out of the brace roots before they ever touched the soil. And that's what you got here, is a sugary substance, the root exudates. Right here, maybe a little difficult to see. You see a little bit of a gelatin area there? That's the root exudates. Now, according to some research, and I've done the calculations, a really healthy corn crop will be pushing out as much as 8,000 to 9,000 pounds of sugar per acre during this time of the year. Up to 70% of its photosynthetic capacity in a corn plant, if it's healthy, is going to root exudates as it's growing rapidly through the middle of the season. Now, the question then becomes, why in the world would a plant waste 70% of its energy and it's not wasted? Because the biology, that's their number one food source. The plant's needs for food, other than the carbon, are the minerals. Biology, they take the sugar. Of course, sugar is just simple. It doesn't have near everything even a bacteria needs to survive. So bacteria feeding on this sugar also has to mine out many different minerals in order to finish its biological process. As the bacteria cycle, as they do rapidly, they cycle and die off, those minerals then become available to feed the crop. And this can happen very rapidly. But corn is a soil building crop if it's healthy. But the problem is, if we go out here and plant corn the end of May, it's pretty much done growing by sometime in August, and the rest of the year the soil is just sitting there. That 8,000 to 9,000 pounds gets used up, the bacteria pretty much die off, and by the time you start to process back over again in May, you're back to square one. To keep it going, you've got to keep some plants out there all year long, or as much as possible. And if we can even build some more active growing and biomass in the shoulder months, previous to planting corn and after the corn comes off, sometimes you can't do both depending on how you use it. But the more we can keep the shoulder months going and live roots through the winter, the more that we can hang on to and build from year to year. Here's a slide presentation that I borrowed from a slide I borrowed from a different presentation. So it all starts with the full capacity photosynthesis. That's the sugar production. When that sugar gets shoved into the soil, it's digested by bacteria, primarily. As I just explained, bacteria have to have minerals. They have to have more than the sugar to build their own bodies and reproduce and all of that. So they mine that from the soil. They make things available that were not available. That's when you get the microbial metabolite nutrition. It's kind of a fancy term for microbe poop. And that is to get your extra energy into the plant. And we think about this, plants can utilize simple ions as their nutrients. Now we know this from hydroponic systems. They mostly rely, some of the later organic systems are getting a little more complex, but your basic hydroponic system relies on simple ion nutrition. Plants take that, they can use it, they can build their frame, reproduce and all that. But if you can get pre-complex nutrition, microbially complex nutrition, that ups the energy potential by several times. It's kind of the equivalent of us going out and stick framing a house, starting with a foundation and putting everything together as a traditional framer would, Or we could, instead of doing that, we could go buy a modular, stick a modular together, and you know how much less energy it takes on site to do the modular process. It's significantly less. Same thing's true with plants. If they get pre-complex nutrition instead of just simple ions, it takes them much less energy to build their frame, do the reproduction and all that they do. The extra energy then, because they don't need all that they're taking up, goes into building fats and the nice things that we want plants to do for us. When that happens, suddenly not only does the above ground portion of the plant have fat, the roots also have more fat. The root exudates contain some fat, and that's where your fungal community starts really kicking in. We talk about bacterial fungal balance. In some circles they're like, you know, we got to push more fungal out there. We use compost teas and get our fungal levels up. Some of that may have its place, but mostly what we find that get the bacteria fungi balance where you want it, it's not a matter of having less bacteria and more fungal. It's a matter of getting more bacteria so you can get to the fungal point. You need to increase the whole system, not just change it. And at the end of that fungal domination then is your humification. That's where you build your stable soil humus that has a long-term stable capacity, things that'll have a half-life. It runs up over 100 years. And that is where you get, well, your biochar, that type of material is kind of the way that some societies and some people have tried to address this, and they've been successful at building a very stable soil. But plants can do the same thing if we get the fungal communities right.